Hi everybody, welcome to Slooh. I'm Paige Godfrey with you again on Wednesday evenings. This is my intro to astronomy course, and it is an audio-only broadcast, but I will be screen sharing to show you some interesting images and diagrams that help explain what I'm talking about. So if you'd like to follow along by watching the video, or also on slooh.com, I'll be clicking around through various things as well. It might be helpful if you're also on the website along with me. But tonight in my course, this is week 3, and from the syllabus, you can see that tonight we are going to go through asteroids and asteroid hunting. So I'm going to click right over to our first diagram of the evening, where let's get through, okay, what is an asteroid? What is a comet? What is a meteor? All these different words that we talk about all the time, and you hear them in the media, and perhaps you're not entirely sure what I'm referring to when I say asteroid. We have a meteor shower tonight. Well, is that an asteroid? What about the meteors, and how is that different from a meteoroid? So this is one of my favorite graphics on this topic. I think it displays it really nicely. You can see how these objects also depend on where they are compared to Earth. So at the top of the diagram, we have comet and asteroid. And so they are two very different things, mostly because of what they're made up of. A comet is a body that's made up of ice and rock, and it originates from the outer solar system, really far away out in the Oort cloud, the Kuiper belt, which we'll talk about a little bit later, but out way beyond the orbits of our solar system planets. And we see these because of their coma, or their tail. When they come near the sun, the ice that is in the comet gets sublimated. Sublimation means that the ice goes from ice to water vapor, skipping the liquid water phase. And this creates a tail that blows off of the comet. You can see in the diagram here, this is mimicking the comet tail or the coma. Whereas an asteroid is also a celestial body from our solar system, but it's a rock instead of ice and rock. It's just rock. So these orbit generally closer in between Mars and Jupiter in what we call the main asteroid belt. Sometimes they also get bounced towards Earth the same way that comets get knocked out of their outer solar system orbit and get bounced towards Earth. And occasionally they bump into each other. They collide, and a collision can create what we call a meteoroid. So taken from the word asteroid, a meteoroid is a space rock that's bigger than a dust grain, like bigger than a piece of sand, but smaller than an asteroid. When two asteroids knock into each other, they can break off pieces of one another, and we create meteoroids. Then, if the meteoroid falls into our atmosphere, when the space rock enters our atmosphere, it starts to burn up our atmosphere, and the friction that it creates when it falls through causes the meteoroid to heat up considerably, and we notice it as a falling star. This is the kind of thing we're going to talk about tonight with the Gemini meteor shower that we're highlighting in about an hour and a half. But this streak of light, we call it a meteor. Now, if a meteor survives the fall through our atmosphere and hits all the way down to Earth's surface, meaning it didn't entirely burn up, we call this piece of space rock a meteorite. And these are the objects that a lot of astronomers study. We have chondrites, chondrules. We study these objects that they tell us about the early solar system formation, because these objects came from not Earth. They came from off of Earth onto Earth, and they're made up of primitive compositions of what our solar system was formed out of. So by studying these objects, which we find a lot of them at the poles where it's undisturbed ground and preserved in all of the ice, we can learn to study about what our solar system originated with. So if we talk about asteroids first for a little bit, the word asteroid actually means star-like. You might have heard the phrase ad astra, to the stars. Asteroid means star-like. And they're important for a lot of reasons, but namely because I mentioned they're clues into the early solar system formation when pieces of them fall onto Earth, or even when we study them from a distance. They can also tell us a little bit about the origin of life. Some of them we know carry water. They might have carried organic molecules from other planets onto Earth. They provide sources for us to mine for metals, should we ever choose to do so. And they also potentially impact Earth, literally. If they hit Earth, that is an asteroid impact, and that could threaten human life as we know it on Earth. And so these objects are really important for us to study. And I've got a jam-packed evening for you tonight, but I have to make sure I keep it quick because we do have our Geminids meteor shower show coming up at 9 p.m., which you can find right in the same situation room that you're in now. And I'll be on again later. But so I've got to fit a lot of information into tonight. So let's just dive right in. The next thing we're going to talk about is the asteroid belt. I mentioned that this lies out between Mars and Jupiter. So if you're looking at my diagram here, you can see Jupiter, where my mouse is this reddish. It's a gaseous body. You can't tell that from the diagram, but it's reddish. It has a lot of stripes on it that represent different weather layers and storms like the Great Red Spot. And then we've got Mars further in, closer to the sun, of course. And in between, we have what we call the main asteroid belt. So the asteroid belt, actually, when it was first found, it was theorized to be a planet based on the pattern in the layout of our planets and the way that they orbit the sun, the dynamics of our solar system. It was first theorized that the asteroid belt wasn't an asteroid belt at all, but just one single planet that was causing the dynamics that we see. But then the large asteroids, two of the main large ones out in the asteroid belt are called Ceres and Pallas. They were found, and then subsequently hundreds more. And so it was clearly not one planet that was making up this area between Mars and Jupiter causing the orbits that we see, but a bunch of different bodies. So then it led to the question of whether the asteroid belt formed from a planet. Maybe there was a planet in the early solar system that was starting to form between Mars and Jupiter, but it got broken up, maybe because of Jupiter's high mass and severe gravity. But actually, the total mass of the asteroid belt, if you combine the mass of all the little objects into one number, is less than the mass of our moon. So it's likely not a broken up planet because it should amount to a much more mass than it does. So now we still are blaming Jupiter for the creation of the asteroid belt, but when the early solar system was forming, and I went through some of the dynamics of that last week on how a solar system formed, a big body, a big massive body like Jupiter has a lot of gravitational pull. And it's to blame for the pieces of rock in the asteroid belt not actually coalescing onto other planets that were forming. So it's possible, had Jupiter not been there, that these asteroid belt rocks would have maybe fallen onto Mars and made Mars a bigger planet. But Jupiter's gravitational pull kept them where they are and kept them from moving around the solar system too much. But it's very representative of the early solar system formation and how this is kind of what the disk looked like in between its very, very beginning, when it was just a protoplanetary disk with no large objects in it, and now where we have massive planets that have coalesced from all of the interactions in the original disk. This is kind of a glimpse of what the early solar system used to look like. And this one object I mentioned, Ceres, is out in the asteroid belt, and it was one of the first ones found that helped to determine it wasn't just one planet out there, but it's actually the largest. It's about the quarter of the size of our moon. It's about 600 miles in diameter, and it's round. Whereas a lot of asteroids, because they're so much smaller, they're not round. They haven't formed into a round shape the way that we described a planet last week, which is massive enough to form a sphere. But it's still too small to be considered a full-fledged planet. It obviously has not cleared its neighborhood. There's a ton of stuff around it, and so it is not a planet. And like I mentioned, it's much smaller than our moon. It's about a quarter of the size, but it is round. It makes up approximately a third of the total mass of the asteroid belt, all by itself. And its iciness is really interesting because a lot of the asteroids in the asteroid belt are not icy. I mean, we assume that they're rocky, especially based on their location in our solar system and their proximity to the sun. Whereas when we talk a little bit later about the Kuiper belt and the Oort cloud, you'll hear that those objects are icy because they are so much further away from the sun. So its iciness is interesting, and NASA launched a mission called Dawn the Dawn spacecraft out to Ceres, and it also visited another asteroid called Vesta. And it found hints of organic material on Ceres, which we already know it has water. And so this is another object which is interesting to us, the way we talked about the Saturn's moon Enceladus last week being capable of potentially hosting life because of its water and organic material. We don't think that Ceres might have life on it, though we don't know below the surface what could be there, but it's possible that objects like this are how life got onto Earth. If it's carrying water and if it's carrying organic material, if it gets booted out of the asteroid belt and crashes into a planet such as Earth, it can spawn life on that planet. So there are 3 different types of asteroids, and they're characterized, well, I shouldn't say there's only 3. There are 3 main ones. There's a lot of other ones. There's actually 9 types of asteroids, but the 3 main ones that we're going to talk about tonight, they're characterized by their chemical composition and the albedo, which is the reflectivity of the object. So these rocky bodies, they don't shine their own light, but when the sun shines off of them, like our moon, like moonshine, we have, we'll call it asteroid shine. That reflectivity and how reflective it is can tell us first what it's made out of a little bit, and also it helps to tell us the size. So the 3 types, the first one is called the C type, where the C stands for carbon. It makes up more than 75% of all known asteroids, so it's the most popular type. And the surfaces of these asteroids are basically black, so they don't have much light shining off of them. Then the next type is an S type, where the S stands for silicaceous. I think I said that word right. It makes up 17% of the known asteroids, and these are made out of a metallic nickel iron and iron and magnesium silicates. So the surface of these S-type asteroids is brighter. And then one of the brightest is the M types, where M stands for metallic, and they're made of mostly pure nickel and iron. Then, since I said there were 9, there are 6 other types, A, D, E, P, Q, and R, but they are all more rare types of asteroids. So if you've already done the math, I've just accounted for most of the percentage of known asteroids with the 3 types. So they're very, very rare, these other 6 types. As actually, New Horizons principal investigator Alan Stern said it very nicely, that I want to quote. He said, "Fortunately, the asteroid belt is so huge that despite its large population of small bodies, the chance of running into one is almost vanishingly small, far less than 1 in a billion. If you want to come close enough to an asteroid to make detailed studies of it, you have to aim for one." So when we look at a diagram such as this and we see how populated the asteroid belt is, we think it must be so difficult to send a spacecraft through the asteroid belt out to the further planets, but we know that we have successfully sent spacecraft out beyond the asteroid belt. And actually, it's really not that difficult. Space is so big that even though this looks so densely populated, if you pulled this out to scale, they are so far away that really we've sent spacecraft through them with no trouble. And as Alan Stern said, if you want to hit an asteroid, you're going to have to aim for it. Speaking of which, as Carl Sagan put in his book, The Pale Blue Dot, which I've cited 2 weeks in a row now, I know I need to pick up another book, but it was just so good. He mentioned that we could land on an asteroid. We do have the technology to do it. And if you remember the Rosetta mission, we have landed on a comet, which, even though they are 2 different things, it's a similar concept of tracking their orbit and sending a spacecraft out to it. But this is why we think that we could mine asteroids for metals if we were interested in doing so. That brings up a whole realm of space politics that we definitely don't have figured out. But should we ever run out of metals on Earth, it's an option for us. And I mentioned how far away these objects are in the asteroid belt, even though they look so densely populated, but these empty regions are actually called Kirkwood gaps. They correspond to orbital resonances with Jupiter, meaning that because Jupiter is so massive and its gravity pulls on these objects in such a forceful way, it leaves these gaps in between the asteroids where there's empty space and then where there's areas that they are way more clumped together. It's because of Jupiter and its tug on these bodies. So then there's another kind of asteroid, which is more newly recognized. as a class of body in the solar system. They're called active asteroids. And this is going to lead me into several things tonight. It's going to lead me into talking about comets and the Kuiper Belt and the Oort cloud, but it's also going to lead me into the Geminids meteor shower, which I'm saving for last. But these active asteroids, what does active mean? So we define this as asteroids that have an orbit like an asteroid, such as we find them either in the asteroid belt or coming from the asteroid belt. But then they have the physical characteristics of a comet, which means that they look like comets because they have the tails coming off of them. But they have orbits that are interior to Jupiter. And we know that comets come from further out in the solar system, which is why they're icy, which is why they have the tails, because when they get close to the sun and the ice heats up, it leaves tails behind. So what on the asteroid is causing a tail? Well, it could be ice. So we have seen, like I mentioned, Ceres, which is an icy body that is in the asteroid belt. So we could have a few of those populating the area. But we also know of some of these active asteroids that have tails that definitely don't have ice on them. So there are other causes that can cause this activity, which is really a mass loss. So we're talking about some form of the mass of the asteroid coming off in the tail. In the case of a comet, it's the ice. In the case of an asteroid, it could be potentially ice-ish, or it could be dust. And so in addition to sublimation of the ice, some of the options are impact. Something bumped into an asteroid and knocked off some of the asteroid out into space, and it follows the orbit of the asteroid because of the gravitational pull, and it creates a tail. Another one is electrostatic charge. So we see this on our moon, where electrostatic forces in space can, like from the sun, like the electrons flying through, can lift some of the dust off of the surface. We see it happen on the moon, and if this were to happen on an asteroid, it might lift it off enough that it actually pulls away and forms the tail. They also can rotate, and if they rotate really fast, we call them fast rotators, they can be unstable, and the instability can cause them to break apart. We also have thermal fracture, which is that when they get too close to the sun, they just get hot enough, and also due to frictional forces of them orbiting the sun, they get hot enough that this heat breaks them apart. And then we also have an interior radiation pressure. And this goes into a whole discussion on formation and kind of stellar formation, but I'll just briefly say that when a body stays put together in space because it has a gravitational force pulling inward towards its center, and it also has a radiation pressure pushing outwards towards the surface. And if those forces are equal, then the object stays put together. So interior radiation pressure can increase when the object gets hot, and that can also cause it to fracture. Only Ceres is the one where we know of ice from spectroscopy, which is the light curve that we get from the object. And so we've seen the reflectivity of Ceres, and that light curve has told us that there's a signature of water gas. So we can be sure that ice is present. And in other cases, we know that these active asteroids are not icy. So there's many reasons to explain why they're active, but it's very hard to constrain which activity is causing the active asteroid. And so further study on this is really important to understand these objects. So this brings me out even further in the solar system to the Kuiper Belt. So if you follow my mouse outwards past the asteroid belt, we pass Jupiter, Saturn. Finally, out beyond Neptune, we have the Kuiper Belt. And this is another similar shaped feature in our solar system. So it's disc-like. It's kind of like a ring around the sun, and it lies out beyond Neptune. There's more than 70,000 trans-Neptunian objects out there, and they're cold. They're so far away from the sun that they're cold, and so these objects are icy. This is where we believe that most of the short period comets, meaning that they have a period of less than 200 years of orbiting the sun, meaning that it takes them less than 200 years to make one complete orbit of the sun. This is where the short period comets come from, is the Kuiper Belt. So something happens out in that outer solar system that knocks these objects in towards the sun, and they come shooting past Earth, They hit near the sun and they heat up. Because they're icy, because they're comets, they leave that icy tail behind them. And this is partially the cause for the meteor shower that we're going to see tonight. But I say partially because there's a teaser coming up about why this particular meteor shower is unique. But here is another diagram to show just how far away the Kuiper belt is from the sun, which is at the center. Our planetary region stretches out to Pluto is about 40 AU away from the sun. And AU I defined last week as an astronomical unit, which is 1 Earth to sun distance. So the distance between the Earth and the sun is 1 AU. Pluto is 40 times that away from the sun. The Kuiper belt is out to about 1,000 AU. And then out even further, we have the Oort cloud. Here is another diagram to show just this large scale. And so this actually puts all the planets in here. So the asteroid belt is between Mars and Jupiter. And then the Kuiper belt is out beyond Neptune. And so we call this kind of the end of the heliosphere. Voyager 1 right now is out in what we call the heliopause, entering interstellar space. And then the Oort cloud, which we're going to talk about next, is even further away than that. And if you look at our nearest stellar neighbor, Alpha Centauri, the Oort cloud really extends pretty close to Alpha Centauri. And the other interesting thing about the Oort cloud is it's a bubble shape. It's not a disk or a belt. And this can be due to its distance from the sun. It's not being forced into a sort of disk ring shape the way the asteroid belt and the Kuiper belt are. It forms much more of a bubble, a sphere around the sun. It extends 1/3 of the way from our sun to the next nearest star system. And it's the source for long period comets. Hundreds of billions of icy bodies live out in this Oort cloud. And long period comets, compared to short period comets, are comets that get sent in around orbit of the sun, but they take longer than 200 years to complete. So if we just look here, NASA has a nice image to show this is the Kuiper belt. So our sun is this yellow dot in the center. The orange track represents a typical Kuiper belt object, what we call a KBO. And Pluto's orbit is represented by the yellow ring here. And we have the Kuiper belt objects. Then, if you zoom out even further, you can see the Kuiper belt is all the way in here, and the Oort cloud is so much larger, really engulfing our whole solar system. I mentioned Voyager 1 being out nearing, well, not near the Oort cloud yet, but on its way towards it. If you read at slooh.com, I have a post about near-Earth, heading there now, sorry. I have a post about Voyager 1 and its location in the solar system and its distance to, my internet is super slow because I'm streaming all the things at one time, so I'm going to hop on over to a page I did have up, but I will go back there later. It's fine. So if I go to our discussion boards, I posted this in Science News under current events about Voyager 1. So Voyager 1, which is currently 13 billion miles away from us, we fired its backup thrusters. Really neat. So if you want to read the full post, you can go here. But the reason that I mention that is that at its current speed, at Voyager 1's current speed, which is about 1 million miles a day, it won't reach the Oort cloud for 300 more years. That's how far away the Oort cloud is. And it does send comets in towards the sun, these long period comets. And of course, you can imagine they're long period because it takes them so long to get from the Oort cloud in towards the sun because it's so far away. And then it's going to take Voyager 1 about 30,000 more years to finish going through the Oort cloud to get to the other side where it'll head on towards Alpha Centauri. Although, of course, it won't be in communication with us beyond another 5 or 10 more years. So it's not going to do us a whole lot of good, but maybe if there's any life on Alpha Centauri, they'll wave to our spacecraft. Although by that time, maybe we'll be there ourselves. So other types of asteroids, which brings us a little bit into what we're going to talk about tonight with the Geminids, are near-Earth asteroids. And a near-Earth asteroid, or a near-Earth object, I should say, is any small solar system body whose orbit brings it into proximity with the Earth. If a near-Earth object's orbit crosses the Earth's orbit and the object is longer or larger than 140 meters across, it's considered a potentially hazardous object. So all known potentially hazardous objects as of this year are potentially hazardous asteroids. So basically what that means is that the objects that are coming super close to Earth that we have to monitor are asteroids. This is why asteroid hunting is so important, and this is why we have a huge team at Slooh who's actually doing it themselves. They're called the A team, led by one of our renowned Slooh members, Tony. And if you are interested in learning about asteroid hunting and being a part of helping keeping Earth safe and finding near-Earth asteroids, you can get in contact with the A team on our discussion boards, and they have training courses to help train you into asteroid hunting and tracking. So actually also Paul Cox, Slooh astronomer, Paul Cox is going to be giving some different courses on practical astronomy and how to use Slooh to see really cool things, our telescopes. And so one of the things that Paul is going to be talking about is tracking asteroids. So I mentioned a potentially hazardous asteroid. There's a fancy acronym called MOID, which stands for the Earth Minimum Orbit Intersection Distance. Basically, when an object, an asteroid, is large enough, larger than 140 meters across, and it crosses our orbit in less than 0.05 of an AU, meaning pretty darn close, and it has an absolute magnitude of 22 or less meaning it's brighter. So the smaller a magnitude number, the brighter an object is. So for example, a magnitude of 20 is brighter than a magnitude of 22. And brightness just really refers to size here. So if an object is magnitude 22 or less, we're talking about objects that are a certain size or bigger. And if they come really close to crossing Earth's orbit, we call them potentially hazardous. They don't have to come necessarily super close to Earth yet, but if they're crossing our orbit really closely, that's a concern because eventually our orbits could cross at the same time. So basically, we don't want an asteroid that could ever get any closer to the Earth than 0.05 AU. We're going to call it potentially hazardous. 0.05 AU is roughly 7.5 million kilometers. And 140 meters, which is the minimum size that a potentially hazardous asteroid would be, is about 500 feet, just for reference, if you prefer the non-metric system here. So if we look on this website, I pulled up the Near-Earth Object website. There are different families of asteroids. And you can see a really nice graphic here that shows their different dynamics in our solar system. So 4 of the different families, one is called AMORs. These are Earth-approaching near-Earth asteroids with orbits exterior to Earth's, but interior to Mars. So the asteroid belt lies between Mars and Jupiter. And so if an asteroid crosses in between Earth and Mars, we call these AMORs. Apollos are Earth-crossing near-Earth asteroids. So these objects actually cross our orbit. You can see the Earth orbit here is in the thick black line, and the asteroid orbit that we're referring to is in the thin black line. Then the next family is an Earth-crossing near-Earth asteroid, but the difference between these two is that their orbit around the sun, the Apollos, is larger. The semi-major axis, which is the distance that the object is away from the sun in its orbit, is larger compared to this one where the orbit is smaller than Earth's. And then the 4th family is near-Earth asteroids whose orbits are completely contained within the orbit of Earth. So they're further in to the sun than Earth is itself. This is another graphic just to show them all at the same time. We have the sun here, the Earth here, which gives the blue, well, I'll say like dark aqua colored orbit line, because then this line's blue as well. And you can see Mars is in this deep red, and the 4 different families of asteroids. And this chunky, rocky belt is the asteroid belt, the main asteroid belt out beyond Mars. I'm trying to see if I can zoom in here. I don't think so. I hope you can see that. So what happens when an asteroid is detected and we need to report it somewhere? Often I mention the IAU, which is the International Astronomical Union. They're in charge of naming all of the objects in the, well, not just the solar system, but in space. They are in charge of, basically, they're the go-to for what do I name this object? How do I define this object? They're the ones that defined what a planet is when Pluto was demoted to dwarf planet. And they also sponsor the Minor Planet Center, which is the go-to for reporting asteroid tracking and comets and minor planets and small satellites. So they're the single worldwide location for accepting positional measurements of comets and minor planets. And they have a website here. You can see the running tallies of different things that were discovered this year, this month, and forever. There's been 17,000 near-Earth objects discovered, 4,000 comets. And so these are observed. When we say discovered, we're talking about observed. They have a list of close approaches. It's a neat website. Another thing I'll point out there is they have a daily minor planet that they choose to highlight. So if you've ever heard of APOD, the Astronomy Picture of the Day, this is another similar thing where every day they pick a different minor planet to highlight. And so today's planet is asteroid, well, not planet, minor planet, is asteroid 3200, which you'll hear about a little bit tonight. And also on Saturday, if you tune in to Paul Cox's show about asteroid 3200 Phaethon, it's the parent of the Geminid meteor shower. So that brings me, well, actually, let me go back to, we're going to start talking about the Geminids now, which hopefully you all are excited for. Let me see if I can just keep, there we go, going back and back and back. So back in October, there was a Earth flyby of an asteroid called TC4. And I took some snapshots of it. Slooh did a live feed. And so similar to tonight, when we're showing live feeds on our show, you can see that, I'll click on one. This one's really obvious. I don't need to zoom in on it, but the trail of the asteroid is visible through the telescopes, and I was able to take snapshots of it. This is one of my favorite ones. It's very dim, so it's not really easy to see, and I hope that the resolution is coming through well enough for you, but you can see the full line here of the asteroid zipping through Earth. They appear as such fast movers compared to the background stars that it's really incredible, the images that you're able to take of these objects. So this brings us all the way to the Geminids, which, as I mentioned, at 9 o'clock, we're going to come back on. Me and Human Spirit contributor Helen Avery and astronomer Paul Cox. We're all going to be here to talk all about the Geminids and to watch some live feeds, the meteor shower. You know, we recommend that you go outside and look up. There should be about 100 meteors an hour that you can see. But, you know, if your skies are cloudy, it's also freezing outside here, well, at least in New Jersey today. I don't know where you're located, but if you're in the Northeast of North America, it's freezing. And so if you don't want to go outside, you can join our live feeds and watch from there instead, from your cozy, warm house. That's where I'll be with my slippers on and some hot cocoa. But the Geminid meteor shower, I mentioned the parent is this asteroid 3200 Phaethon. And so if you know that meteor showers are typically caused by comets, then you're wondering why I'm calling the parent an asteroid. And you're right. I teased about this earlier, but that is so one of the coolest things about this meteor shower that is being hyped all over the media is, of course, how many meteors you can see. Yeah. What I think is so cool about this meteor shower is that its parent is an asteroid and not a comet. So I mentioned a comet's icy. It gets kicked out of the Kuiper belt or the Oort cloud. It gets sent in towards the sun. It gets too close to the sun and it heats up. The ice sublimates into water vapor, which pulls off of the comet, but stays closely behind it because of the comet's gravitational pull to it. And it creates a tail, the coma of the comet. And this tail, it's basically debris that's left. And if it's in the orbit of Earth, then we pass through it. And when we pass through it, the pieces heat up in our atmosphere. The debris heats up into our atmosphere and it burns up, and we see what we call shooting stars, which hopefully by now you know are not actually stars. They are just pieces of rocky and icy debris that were left over by a comet getting too close to the sun, and we happened to cross through the debris trail. But back when, early astronomy, when stargazers were looking up and saw these meteors, they didn't know that it wasn't a shooting star, that it wasn't a star flinging itself across the sky. So that's where we get the shooting star name from. But so this is a comet causes a meteor shower. But I mentioned active asteroids too. And so an asteroid can get too close to the sun as well and heat up and break up. And then there's rocky debris left behind it in a tail. And the Earth, if it orbits through that tail, then we see a meteor shower. This meteor shower, the Geminids, is one of the first meteor showers that we found out where the parent was an asteroid and not a comet. Then it's so cool. And it's called the Geminids because when you look up at the sky and you want to see where the meteors are coming from, you should be looking towards the constellation Gemini. We'll talk a lot more about that tonight. Helen has some really cool things to talk about with the Gemini constellation. And if you tuned into her show on Sunday, she talked all about the Gemini twins. But the Geminids meteor shower, because there's so many meteors, you don't necessarily have to look towards the Gemini constellation. You should be able to see them all across the sky. But that's where the meteors look like they're originating from, is that area of the night sky. And so we call it the Geminids. And I'm also going to talk, if you tune in again at 9, I'm going to talk about the parent of the Geminids meteor shower. So the grandparent, which was... I'll go to that now as well. A Illuminations post. Let me just go straight to the Geminids. Make my life a little bit easier. So we have featured topics, and so we highlight featured topics based on what we're featuring this week at Slooh. And so this week we're talking about the Gemini meteor shower. So I can just easily go right here. And I made a post about the grandparent of the Geminids. And so if you don't want to wait till 9, you can go here and read it for yourself. But otherwise, I'll be talking about it later. And that's all that I'm going to say for tonight. I'm going to wrap up a little bit, I guess not necessarily early, but give you some time to go get a snack before you come back at 9 for our Geminids meteor shower live feeds. And if you're interested in hearing more Intro to Astronomy, then next week on December 20th, same time, same place, you can join me to learn about our nearest stellar neighbor. I'm going to talk about the Alpha Centauri system, the one that I showed. Nope. There, the Alpha Centauri system is our nearest stellar neighbor, the nearest solar system to ours. So I'm going to talk all about that and why it's important to study, what we know, what we don't know, and why we need to learn as much as we can, as this solar system peeks into our own backyard here. So I'll wrap up now, and I hope that you've enjoyed hearing all about asteroids and meteors and comets, and I hope that I cleared some of this up for you before the meteor shower comes on tonight. If you have any follow-up questions, feel free to post them on our discussion boards under my course thread, and I'd be happy to answer them. You can also post questions that you might have for tonight's show if you go under our live cast discussion board thread, and we will all try to answer them when we're online in an hour. So we hope you join us back tonight to see the meteor shower, and go outside and look up at the sky. It's pretty awesome out there.